All right, so what's going on, y'all? This is problem 215. This one looks complicated, but it's really not. You'll see why. Let's go ahead and get started. It reads, determine the nodal displacements, the forces in each element, or the local element forces, and the reactions using the direct stiffness method. So let's go ahead and get started. All right, so first step, this problem, just like I mentioned, is not complicated at all. It just looks a little crazy, but the only thing about it is it can be tricky. So you gotta know what you're doing. And what I mean by that is, well, you'll see, but the nodes, the way they place the nodes, you gotta be careful how you do the global stiffness matrix and then the local element forces at the very end. So let's just start it like always, right? There's 4 nodes, so that means there's gonna be 4 forces, F1x, F2x, F3x, and F4x. Okay, that is equal to the global stiffness matrix. That is nodes 1, 2, 3, and 4. Nodes 1, 2, 3, and 4. Give yourself some space because some numbers could be pretty big. So look, this one's between nodes 1 and 3. This is elements 1, 2, and 3, the spring. So it really doesn't matter how you name it, right? What matters is what nodes are they in between. I mean, you know what I mean, right? And what nodes are to the side of the spring. So in this case, let's do the first one. That is 500 as the value, kilonewtons in this case. Everything's in kilonewtons and meters. There's no reason to convert to just newtons or whatever, right? So in this case, we'll leave it 500 and 1,000, but in this case, just 500. So it's between nodes 1 and 3. So you're gonna go to nodes 1 on your matrix, 3 on your matrix as the columns, and then 1 and 3 on the rows. So the first one is 500, right? Because the value is 500. Then it's negative 500. Then negative 500, and then 500. Now the reason that they're negatives, I forgot why, I gotta look in the book, but point is it's positive, negative, negative, positive, okay? If you're really curious, do some research on YouTube or look in your book. I forgot why, but I'm too lazy. I already graduated, so I don't really need to. So it's between nodes 1 and 3, so that's how we got those, right, okay? Second one, it's between nodes 2 and 3. So we go here, 2 and 3, 2 and 3. That value is also 500. So let's go 500, negative 500, negative 500, and 500. There's already a 500 there, so we're gonna add them, and it becomes 1,000. Now, 3 and 4 for the third one. Okay, so it's between nodes 3, 4, 3, 4. That value is 1,000. So it's 1,000, negative 1,000, negative 1,000, and 1,000. There's already a 1,000 here, so we're gonna add them. That becomes a 2,000. Okay, that's a 2. I'm not gonna erase because I'm lazy. Negative 1,000, negative 1,000, and 1,000. Fill in the rest, right, with zeros. So we're gonna have 0, 0, 0, 0, 0, 0. Forgot to write the displacement vector. I usually do that before I do all this, but it doesn't matter. U1, U2, U3, and U4. So a displacement vector, for those that don't know, it's just how much is the node gonna move at the end once you apply these forces. So check it out. Let's do the boundary conditions at the nodes. 1, 2, and 4 will not move regardless of how much force you put at node 3. They're fixed, so they're always gonna be 0. Well, assuming the system doesn't break. But let's go ahead and, man, the eraser. There we go. 0, 0, 0, and all right, got pulled away into something, but continuing. So we did the nodes at the boundary conditions, right? U1, U2, U4 will not move. See, I messed up already. It was actually U3 that's gonna move. not U2. So this is 0 and U3. Then the forces, we don't know the forces at 1, 2, or 4, but we do know it at 3. There's 2 here, 2 here. That means it's a positive force going on at F3x. Right? So if you haven't watched the other videos, you know you're doing something right if you know either the force or displacement at that node. So in this case, we don't know force at 1, but we know displacement 0. We don't know 2, but we know displacement 0. We know the force at 3, so we don't know displacement. And then we don't know the force at 4, but we know displacement 0. So that means you're on the right track. Step 2, F1x is equal to, it's 500 times 0, 0 times 0, negative 500 U3. And that's why this problem is easy, because all the U's except U3 are 0. So everything is going to be in terms of U3. F2x will be negative 500 U3. Right? 0 times 0, 500 times 0, negative 500 U3, 0 times 0. F3x, which is 4 kilonewtons, it's negative 500 times 0, 2000 U3. And then negative 1000 times 0. And finally, F4x, it's the same thing, negative 1000 times U3. So we got 4 equations, 4 unknowns, but like I said, in every problem that you come across for springs and all that, you always stay away from the force equations, because you got to find displacements first. In this, there's cases where there's going to be 5 unknowns, if like other videos that we've done, and you'll have 3 equations that we know the force in and we don't know displacement. So it would be those 3 equations that you focus on. In this case, it's just 1, and it's straightforward, right? Just solve for U3. So U3, just by looking at this third equation, U3 will be equal to 0.002 meters. It's just 4 divided by 2000. So now that you know U3, you can just plug into all of them. This, like I said, this problem is very, very easy. I'm not sure why. I guess the point of this problem was to try to trick you with the nodes. You'll see what I mean. But for now, we appreciate the easy problem. Force 2x is equal to force 1x, right? They're the same. Negative 500 times this. And that is going to give you negative 1 kilonewton to the right, or 1 kilonewton to the left. Negative to the right is the same as left, positive. Does that make sense? Positive to the left, yeah. So that's the answer for force 1 and 2. Cool, we'll box it up. Then find force 4. It's just double, right? Negative 1000, negative 500 is just this times 2. So it's going to be negative 2 kilonewtons to the right, which equals 2 kilonewtons to the left. Now, before we continue to the local element forces, let me move it up just in case you can't see. But before we move over to the element forces, we got to verify these numbers. So like I said, U3, it's kind of hard to verify because we're not spring experts or whatever, right? There's no way you can know it's going to move just that distance. But we can verify the forces. We got a total of 4 kilonewtons going to the right, at node 3. 2 here, 2 here. That means the sum of all this one, and this one have to equal 4 kilonewtons to the left. This problem, it's an equilibrium, obviously, but it's equal, it's symmetrical. There's 2 500s here. There's a nice 2 at each side. There's 1000 here. I really can't explain how it's symmetrical. Maybe you might be able to see it too, but it really is. So it kind of makes sense how these 2 forces are equal, and it kind of makes sense how this one's double those. Does that make sense? So look, we got 1 going this way, 1 kilonewton to the left. We got 1 going this way, and we got 2 going this way. So I hope that makes sense. Maybe you could see it, but I mean, either way, they both, all 3 nodes, 1, 1, 2, they equal to 4. So you did something right. So just wanted to kind of see that, how it's kind of symmetrical. So let's go ahead and get started with the element forces. Now this is where it could get tricky. Let's do the first element. An element is a spring. So this first element is between nodes 1 and 3. So that means it's F1x, F3x. In the other problems that if you've been watching the videos, it's been F1, F2. In this case, it is not. You gotta be careful how you set that up right there, because that will mess you up. So you're doing nodes 1 and 3, that's why. So that value of the spring is 500. So 500, negative 500, negative 500, and 500. And it is between nodes 1 and 3, so you use U1 and U3. U1 is 0, U3 is 0.02. So cool. Then you just solve for them. So F1x of element 1 is equal to negative 1 kilonewton, to always to the right. For local element forces, never change them to positive or negatives, always to the right. You'll see why. So it's 500 times 0 plus negative 500 times this. That's how you get that. So F2, oh, you see, F3x, not F2x, of element 1, that is, the signs just switched. Now it's negative 500 and 500, so the answer is going to be the same, except it's just positive. And again, always to the right. These will always be to the right. Remember that. Assuming you're following my method. All right, so we got the first one. Second one, it is between nodes 2 and 3. So F2x, F3x equals, and that value is 500. So it's 500, 500, negative 500, negative 500. And that is U2 and U3 because it's between nodes 2 and 3. So that is same thing, 0.002 and 0. Okay, so for F2x of element 2 is equal to negative 1 kilonewton to the right, always to the right. F3x of element 2 is equal to 1 kilonewton to the right. And last one, element number 3, that is between nodes 3 and 4. So F3x, F4x equals the matrix. It's 1,000 down. So it's 1,000, negative 1,000, negative 1,000, and 1,000. That is between nodes 3 and 4, so it's U3 and U4 this time, so 0.002 up top, and 0. F3x times element, not times, of element 3 is equal to 1,000 times that. That is positive 2 kilonewtons, going to the right, always. F4x of element 3 is equal to negative 2 kilonewtons to the right. Now let's verify them. Now this is how you verify element forces for those new to the channel. So I don't know how to explain it. I know how to tell you, just do it, right? But I guess if I had to explain it, it's just the sum of the elements of each. So in this case, right, you got F2, F3 here, F3 here, F3 here. So when you sum all the F3s, you have to equal your big F3, which is 4. So you'll see what I mean. Hold on. So in this case, our big force of 1, it's right here. We found it. Negative 1 to the right. That means when you add up all the F1s here, the little F1s, you're supposed to get negative 1 to the right. So we got 1 right here, negative 1 to the right, and there's no more F1s. So that means F1 is verified. Check mark. F2 is also negative 1 to the right. So add all the F2s. We have a F2 right here, none here, none here. That's F3, remember. Negative 1 to the right. So verified as well. Boom. F3 is 4. So add all the F3s, you should get 4. We have a F3 right here, that's a 1. F3 here, that's a 1. F3 here, that's a 2. Add them all up, you get 4. That means boom, verified. And finally, F4x should equal -2 to the right. Okay, so there's only one F4, it's right here, -2 to the right. So that means we did this problem correctly. All the local elements were verified, the forces were already verified, remember? And I guess the biggest takeaway here in this problem is knowing how to set up the global stiffness matrix. Be careful, it's between nodes 1 and 3 in this case, so it's row 1, row 3, and column 1, column 3. And then also here, remember F1x, F3x, because it's between those nodes. But yeah, easier problem, just a little trickier, but there it is.